Hey, welcome back. Today we're going to be talking through how to set up an experiment for physical pendulums, and this is specifically for AP Physics E Mechanics. This shows you how to handle a experimental design question, and it's actually super important to be able to do this as you will have one of your FRQs will have an experimental design component. In other words, you are going to be asked to design some experiment for some important set of concepts we've been looking at. This is based off of a video that the College Board has done, so you can bet that this is something that you should know how to do here. And I'm going to show you in a little bit more detail about the background for where some of these things are and connect some of the loose ends. So I do want to start by saying a physical pendulum, we do now have an equation for the period of a physical pendulum on our equation sheet, and that's going to be down here, so we need to be ready to deal with that. And I have done a previous lesson on how to do a procedure efficiently, and I'm going to demonstrate that here, but if you want more information about that, you can take a look in the upper right about now. But let's continue. I'm going to show you exactly how to do everything you need to do here. I will say this is about where we left off on our last video of the series, and I want to explain briefly, initially, where that applies. Like, where does that fall into anything? I had said that this is an important equation to be able to end up with for physical pendulums because it's going to be integrated into FRQs. So let me show you how that could apply. Okay, and so first, before we do anything else, I promised I would show how this equation that we left off with last lesson is actually useful. So I had said that you are expected to be able to derive this when working with a physical pendulum. And so what we can do is, this is on your equation sheet right here. This is the position equation for simple harmonic motion. From this, you should be able to derive 5 other equations: the velocity, the acceleration, and the rotational version of those as well. So if we were to sub this in over here and think of this as a rotational version, first of all, I do want to point out that I'm going to ignore phi for this problem. If you have no information about the offset, the phase shift, then you don't need to effectively worry about it. Most problems you're going to kind of ignore the phase shift. And I'm going to write this in a rotational sense. And that's effectively how that last equation that we came up with from last lesson is going to be useful. You should be able to write this. I predict right now that you will see a future FRQ, maybe even coming up this year, on whether or not you can do this kind of thing right here. So I'm just going to write future FRQ on whether or not you can do the material from last lesson, sub it in here, write the rotational version, and then solve for something you are asked to solve for. If you want to learn more about how we derive that equation, I could put a link to the previous lesson in the upper right about now. But let's continue with this and think about how we would write a procedure here. So conceptually, it's really important to think about, how do I go about doing this as a student? How do I write the procedure? And we say that there is a backwards mapping. In teaching, there's a backwards mapping. You have to know where your goal is, and then you plan backwards from that goal, so to speak. And that applies here too. We need to think about our equation. And there is a sequence here. First, you got to select the major equation that you're going to be working with. Then you need to write what your knowns are. Your knowns are going to be measured in this case, right? So we have to figure out how we're going to measure those and write about how we're going to measure those knowns. And what our unknown is, we really usually just have one. So I'll just say unknown. And then after that, then we can write our procedure, right? Because we don't want to start with writing the procedure when we don't actually know where we're going with this. So we have to be careful and figure out where we're going. Now, this equation, I'm going to say right here that I just circled, that is now on your equation sheet. So this is new. So we do have our major equation essentially already given to us. If we want to solve for the moment of inertia for this system over here, like the hoop that's rotating offset from its center of mass, then you could use this equation. So let's think about what we would do with this. In terms of what we would need to measure, all right, let's think about the things that we could measure. We actually could measure the period. It wouldn't be hard to do. If you had a physical hoop and you set it up at some maximum displacement and allowed it to oscillate back and forth, like you could do that, say 10 times, divide that time by 10 and get the period, right? So that's how we would go about doing this while trying to eliminate a bunch of error. Mass would be easy to measure, right? You would just have, like, say, a digital scale and measure that. This D, let's talk about this D. This D is really, really important here. So in this case, I'm going to label some things off to the left. This is what I would call the axis of rotation is what we would call that over here. But you could also call this a pivot point. So this is a pivot point or an axis of rotation, and this right in the middle is going to be the center of mass. So that's going to be our center of mass, and the difference between these, maybe I'll go over this with white so we can see the writing here. Okay, now what I want to point out is this distance right here, we're going to call it a couple different things. In our previous work, we called this D. Here we could call this our inner radius. If you think about it, that's what that offset would be. And I use that term offset specifically because we're going to use that as a concept to think about what's happening here. Oh, I do need to point out that importantly in the equation that we're given over here, it's written as a lowercase d. So unless the problem tells me otherwise, I'm going to try to use lowercase d when doing this. But it's really important to notice here that that could be measured on your device. Like this physical pendulum, you could measure the inner radius, and that would be our little d value right there. Really important to recognize that. All right, let's continue with the problem. So on the left over here, I've got a few things to think about. Just you want to be careful. You want to talk about the things that the object needs to be measured, and you need to measure it with different instruments and what exactly you're going to be measuring and putting in your data table. So it's actually really important that you get all of these. Remember, we said we wanted to measure the period. So let's start with that. Just working from left to right across the equation that we know we need to use. So now we can write our procedure. So we're going to say okay, so this is something we could write. We could measure the time for 10 complete oscillations with the stopwatch in seconds. If the equation down in the lower left right here, I'm writing arrows by it, is the one that we would use, we would actually want to measure that theta max and start with that, right? Like using a protractor, measure the maximum displacement in terms of the angle from the equilibrium position, something along those lines. But we don't need to write that here. We're just measuring this period. And to do that and to eliminate some of the uncertainty and inaccuracy, we're going to do this over 10 complete oscillations. What else do we need to measure here? Well, we're going to need to measure the mass. And it's really important that we mention the instrument, as you see on the left-hand side. Like, we got to talk about what are we measuring the mass with. So we would measure the mass with preferably a digital scale. And you want to end up in kilograms with that. And what else do we need to measure here? This D, like we talked about down below, really crucial that we measure the D value. That, again, is the distance between the axis of rotation and center of mass. In other words, that is our radius. That's our inner radius for this disk. So we would write something like this. So this effectively could be our procedure, or the vast majority of our procedure right here. Remember, when you're writing your procedure, you don't want to say too much about the analysis. You don't want to get too much into the analysis at this point. You want to save that for later. Usually these FRQs are going to have an intro experimental design part and then a later analysis part. So next, let's talk about how you would go about solving for the moment of inertia for something like this when you have everything measured. So we can start by writing the equation that you see right there. And here I'm going to choose to use D. Again, get into the practice of whatever the variable that the College Board is using for the problem, that's what you want to use. And if I'm not given anything else in the problem, then I'm going to use the variable that I see in the equation here. So, and if we want to isolate for I, remember I here is going to be our unknown. The first step, if your unknown is within a square root symbol, it's just going to be to square everything. So if we square everything, we end up with t squared is equal to 4 pi squared, and this is what we're ending up with. Okay, now the next thing that I want to say, if you want to do this all in one step, I'm going to need a little more space here, so I'm going to move this off to the side. But when you are trying to isolate and have a bunch of things to get rid of that you don't want, think of the phrase multiply by the reciprocal. In other words, if we want to get I by itself, we're going to multiply by the reciprocal of everything that we have. 4 pi squared is up top in the numerator, so we need to write 4 pi squared down below. And mgd is in the denominator, so we're going to write mgd in the numerator up here. And if we do that, then we end up with quickly isolating and getting rid of a bunch of stuff that we don't want. Just a preference thing, I'm also going to switch where my unknown is going to be, so we end up with I is equal to this. Okay, now we've gotten a certain distance into the problem, but it's really crucial, and I'm going to need some more space, so I'm going to move this down here. It's really crucial that we don't stop here in terms of our understanding what's going on. Remember, there was an offset. So hopefully using the term offset is a trigger, and you can try to remember back in Unit 5 and Unit 6 when we're talking about something that is not rotating about its center of mass, but it's rotating about an axis of rotation that is offset from the center of mass. So what is the name of the theorem that we need to use to be able to understand how to do this? Well, that is called the parallel axis theorem. So this is like I total, we could say, but we need to break this down into its components. So we have the I for the center of mass, the moment of inertia or rotational inertia for the center of mass, plus I could call it like I offset. Okay, and then we're left with the same information that we had before on the right side. Let me just paste that down. Let's think about what this offset is going to be. So we've got I center of mass, but remember this is like mr squared in general. Okay, so it turns out that the general equation for the moment of inertia for an offset is simply going to be mr squared when we're using this parallel axis theorem. Now let's think about what this r would be in context of what we talked about previously. So I'm going to move the screen up a little bit up and take a look in the upper left right now. What do we think this offset is? Hint, take a look at that. It's the difference between the pivot point and the center of mass. What would we measure that to be? What do you think that would be? Well, that's going to be the inner radius. That's really crucial to be able to spot. And so we could write this in a couple different ways. And instead of an r squared, we could say radius inner squared. That's one way of doing this, or we could write this to be similar with what we see in our previous work in the equation. We could write it as something like this is equal to our previous work on the right. Okay, so now we need to take this and again just simply isolate for our unknown and we're good. So let me show you what I'm talking about here. And that's what you're going to end up with. Don't extend this fractional symbol over to the next term on the right-hand side. It should not extend over there. But that's how you would go about isolating for your moment of inertia or rotational inertia for the center of mass for this kind of object. And that's how you would think about this. And so this is the second in the series dealing with physical pendulums. There is going to be a third in the series as well, so I'll talk about that in a moment. I do want to say I've done screencasts on an entire year of physics as well as almost the entire year for AP Physics C Mechanics. So if you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.